Okay, so welcome back to the afternoon session. We have 3 talks before the coffee break and 2 after. And it's a great pleasure to have Misha from Harvard here opening the session.
Yes, thank you, Hannes. So thank you, the organizers, for invitation. It's always a great pleasure to be here and to see how this community also evolves with time. So this session will be about using Rydberg atoms for building quantum machines, quantum computers, and quantum simulators. And often when I actually give talks to people who are working in this field but not using atoms, I often start with this slide, with actually is basically a starting point for many of our experiments. So this is basically a picture of magneto-optical trap, which is the basis for all cold atoms experiments virtually. And here, this picture shows about 10 million cold atoms. And what it means is that if we somehow are able to use each of these cold atoms to encode, for example, a qubit, so we actually end up with the system which has a lot of qubits. So in fact, if you want more, there are ways to actually create larger ensembles of cold atoms. So the only challenge which stands between this picture and building a large-scale universal quantum computer is basically an efficient classical control. And that's what this talk will be about. The theme of this talk is how to actually tame atoms, how to control atoms to build quantum information systems. So the approach that we will be taking involves essentially building quantum systems atom by atom. And what we'll do is we'll start with the cloud of cold atoms, and we'll use optical tweezers to grab atom one at a time. And actually, rather than just using one tweezer, we're now using thousands of tweezers, and we create this kind of arrays. Because when we grab the atoms, and if we focus tweezer tightly, each of these tweezers can host at most one atom. We still have kind of disorder in the system because some traps end up filled and some are empty. So to get rid of this entropy, what we do, we take a picture of the atoms and rearrange them in a kind of desired configuration. And so with that, we end up with tweezers which are a couple of micrometers away. And at this point, the atoms do not interact at all. So to make them interact, we make use of the Rydberg atoms. We excite the atoms in the Rydberg states. And this is a project that we started, almost 10 years ago, actually, with Manuel and many other people who now went on to start their own groups. But this is a project which is still going strong. It's collaboration between my group, the group of Markus Greider and Vladan Vuletic. So let me just mention one specific feature which we like to use from the Rydberg physics, and this is Rydberg blockade. The idea of Rydberg blockade is the following. So suppose you drive atoms into the Rydberg states resonantly, and initially the atoms are sitting very far away. So in this case, I will just undergo individual independent Rabi oscillations. But if we bring these atoms close, then at some point, the strong interaction between the atoms, which actually is proportional to the level of power of principal quantum number, will take over. And so what will happen is at this point, we will be able to excite one atom or another, but never both. And so basically, that's the idea of the Rydberg blockade. So that says that simultaneous excitation of the Rydberg atoms is blocked at distances smaller than this Rydberg blockade radius. And it turns out it's actually a very good mechanism, very robust mechanism to entangle atoms because it's insensitive to motion and position of the atoms. So in what follows, we'll follow this kind of general protocol where we will assemble some arrays of atoms and we'll excite them with the laser pulses, flip the ground, internal states, sometimes flip the hyperfine states, but sometimes excite them to the Rydberg states. And then after the evolution, we'll just take another picture of atoms in this way, in a state-dependent way. And this is basically how our, quantum, system, quantum processor or quantum simulator will work. So I should say that this is now truly an exploding field. So there are a couple of hundred experiments under constructions around the world, and at least 6 companies are trying to commercialize this technology. So starting from about 2020, for about 2.5 years, we actually were operating what we call second generation atom array in our lab. And so in this second generation, we were able to create 2-dimensional systems up to about 300 atoms. So what is shown here is basically different, ordered configuration, different lattices. So we can also create disordered configurations. So for example, like here is the picture, the pattern that you would like to create. And so we press a button, and here are the atoms. So we, in these experiments, we use 2 types of optical traps. One is a stationary traps, which are generated by this device called special light modulator, basically a computer-generated hologram. And then we also use 2 cross-acoustoptic deflectors to move the atoms around. And as I already mentioned, so in this case, we can actually work with about, we could work with up to about 300 atoms. And so one very natural modality for that is to use it as a kind of analog system. Here is an example. Suppose we start with a square lattice, and each atom now is driven to the Rydberg state resonantly. So you have this Hamiltonian, which is basically a single atom driving term. This is a detuning term, which actually also can affect as a chemical potential. And this is the interaction term. That's the term which actually really enables this blockade. And so, for example, if you position atoms and excited the state such that only nearest neighbor is blockaded, then if you, for example, start with atoms in the ground state and negative detuning, so it turns out to be then the ground state of this Hamiltonian. If you change the detuning slowly from negative to positive, then once in a while you see pictures like this, which is basically perfectly ordered antiferromagnetic state. Admittedly, this is not what happens on every shot. So on any given shot, you have sometimes some domain walls. So you can actually evaluate, for example, correlation function, density correlation function, and this shows that correlation spread across the entire array. We can also look at these images microscopically. So, for example, here, what you see is that a state like this, even though it doesn't occur very often, actually it's still the most probable. This is a complementary state shifted by one lattice side. And moreover, not only we can kind of study, like slow change in detuning, we not only study like statical properties, we can also study dynamical properties. For example, by varying the speed with which we change the detuning, we can see that this correlation grow at a different rate. And it actually turns out that, if you use the ideas of kind of universality associated with quantum phase transition, you can actually, by rescaling all of these curves, they collapse. And actually from here, you extract things like, for example, critical exponents, which are kind of the determining key features of this quantum phase transition. So it actually turns out that this is what we have done here. We exact response to observation to this 2+1 Ising quantum phase transition. It's actually a very well-known kind of textbook transition, but apparently has not been observed prior to this work. And so with this kind of system, we actually had a lot of fun, and we explored all sorts of things, exotic phases, studied dynamics, pushed the systems far from equilibrium. We actually explored topological physics. For example, we created for the first time topological spin liquid and kind of small baby kind of topological qubit. But I will talk today about some of the more recent kind of developments involving applying this kind of system to accelerate combinatorial optimization. And in particular, I will focus on describing this kind of new application of these ideas to this kind of new frontier, which sometimes we call quantum error correction frontier. I should also mention that we have more than one system of the type that I described in town. And in fact, just across the river in our startup company, QuEra Computing, there is another system which is very similar to what I just described. And since last November, it became publicly available on the cloud. So actually, there are a couple of papers already published using this. So let me just give you a couple of examples, and I'll start with this idea of kind of using this quantum dynamics to accelerate combinatorial optimization. So this idea actually is due to our session chair, and who recognized very early on that actually this Rydberg blockade is actually intrinsically connected to one hard combinatorial optimization problem, which is called maximum independent set. And in this problem, you're basically given a graph, which graph has vertices which are connected by edges, and you would like to color as many vertices as possible, for example, color them red, but you are not allowed to color the two vertices which are connected by an edge. And so basically this MIS problem essentially involves finding the number, what's the largest number of the vertices you can color. And so what is shown here is an example MIS problem on a unit disk graph where basically vertices are connected within the if they are within the given distance. So it actually turns out that this problem, even for this restricted set of instances, is actually NP hard. And it's actually also turns out to be it's actually an important practical problem. But as I already mentioned, so long as you kind of followed my talk so far, you will immediately recognize that this problem is intrinsically connected to this Rydberg blockade problem. The Rydberg blockade problem we often want to excite as many atoms as possible without violating this blockade constraint. And so this is actually D is basically blockade radius. And indeed, as Hannes initially noticed, this classical part of the Hamiltonian of a Rydberg blockade basically, is very similar to the classical cost function of this problem. And what we'd like to do now is we'd like to kind of utilize this observation to try to basically explore if we can use quantum dynamics to somehow speed up this, combinatorial optimization. And the key word here is this hardware efficient approach. So we would like to utilize this kind of correspondence that, to really kind of do it efficient. So the way how we do it is we start with the unit disk graph, and basically we map it into this Rydberg system by essentially putting the atom on each vertex of this graph, and then kind of arranging connectivity by just determining this Rydberg blockade radius. So basically all of the basically atoms or vertices, if you want, within this Rydberg blockade are connected. And then what we want to do is we want to basically start with all atoms in the ground state and then excite as many of them as possible subject to blockade constraint. And this by definition will give us a solution to this problem if we can do it well. Now, of course, there are different types of excitations which one can create. And so in this specific case, which I will show, we use this kind of variational adiabatic excitation. We try to excite the system slowly. But we also change the rate with which we excite in order to basically go in particular slowly across the phase transition. And we also use the closed loop optimization. So we run the experiment, see what how many atoms we excite. We change a little bit the excitation, and so that's was part of that. And actually, in this when you do this closed loop, you actually have to define figure of merits of your success. And there are various things. One could look at approximation ratio. One can look at probability that you actually solve the problem. And so then with this within the setting, what we did is we basically threw hundreds of graphs to this problem, and actually its kind of result was quite interesting. Sometimes graphs of the similar size, you just change one or two vertices, the hardness changes by orders of magnitude. So I'm not actually going to go into details about that. I will just talk about one aspect, and this is benchmarking against classical algorithms. So in this work, we focused on specific, specific family of algorithms, which is actually called simulated annealing. And so in simulated annealing, what you do, you effectively classically cool the Hamiltonian to the ground states by stochastically flipping the speeds. That's the essence of the simulated annealing. And what we can do now is we can basically optimize the simulated annealing and try to compare it with how our quantum machine works. And so here are, just few different instances, different colors here. And so what we see is that there are two regimes. One is this high energy, high, like low approximation ratio regime, where all of these curves are basically proportional to each other as you vary the depth of your circuit. But actually then there is a regime where you enter high approximation ratio, kind of low energy regime, where some interesting things start to happen. So in particular, in some cases, this simulated annealing literally gets stuck, and basically remains stuck for a long time, where in some of these cases, the quantum machine basically solves the problem. So what is happening here? And why some of these instances are harder than another. So we actually understand it quite well now. So it turns out that the instances which are hard are the instances which have a lot of approximate solutions, they're pretty good solutions, but very few actually have, perfect solutions. And so what happens then, simulated annealing basically ends up kind of doing the random walk on this within the subspace of approximately good solutions, and actually it really has no gradient here, basically it only can kind of, make a transition to the actual solution if it really comes very close with its edge kind of leading to this solution. And so it turns out that in this case, one can actually prove that this, simulated annealing, has exponential scaling, and it's determined by this hardness parameter, which is basically a number of these, for example, solutions with MIS -1 divided by a number of edges leading to MIS, and this actually scales exponentially. This hardness parameter scales exponentially with system size. So at this point, having understood it, what we could do, we could just take the 2% hardest graphs and then throw them again to the classical and kind of quantum system. And here are just two examples. So classically, all of these graphs are hard, so they all enter this kind of plateau. But quantum mechanically, sometimes these graphs are hard, but sometimes quantum system just solves this problem. But again, these are just two instances. We need to look at many of them. So here is a performance at a fixed depth as a function of this hardness parameter, and what we see is that basically the red points are quantum and the blue are classical. So quantum machine outperforms classical for many instances, but not for. And so in fact, for some of them, quantum is worse than classical. So what's going on? So what determines quantum hardness? So it actually turns out that quantum hardness is determined, not surprisingly, by the energy gap, by the smallest energy gap. And the way how we notice this, how we see this, is that basically when you optimize the quantum algorithm, it actually slows down exactly at the point where the gap is smallest, at least for instances where we actually can find the classically the spectrum here. So and one can also plot then basically the probability to find the MIS as a function of the for a fixed evolution time as a function of the gap. And what we see is that for many of these points, you have very nice Landau-Zener scaling. So it basically really shows that hardness is limited by adiabatic gaps. But there are some instances where these two parameters, gap and PMIS, are uncorrelated. Actually, it turns out these are the instances where we are just going too fast, where our evolution is too fast to resolve this minimum gap. And so in this case, we basically kind of violate the speed limit. So you cannot, basically the system does not see the entire, the evolution does not see the entire graph. And so using this, we can actually analyze this data, our data, and in particular, if we focus on these instances where we are below the speed limit, what we see for this class of instances, we actually see a superlinear, nearly quadratic speed up, and which emerges in this kind of deep circuit regime, in a regime where you basically, the quantum system basically can explore this entire graph. So this was the observation from last year, and actually since when we have actually learned a lot. So inspired by that, we started doing kind of more detailed theory. In fact, it turns out that one can actually obtain provable speed up by all unit disk graphs by modifying the Hamiltonian a little bit. So we're also looking for opportunities for faster than quadratic speedup using something which is called overlap gap. It's a concept from computer science. And in particular, we are now exploring scaling up. So we're thinking about, going beyond unit disk graph. Maybe Hans will talk about that a little bit, but also about kind of ideas of controlling and mitigating errors. And actually, this is something that I want to now focus on. So up to now, I've been talking about encoding quantum information into this ground Rydberg states, but we knew since already many years that this is not the most optimal. So, and actually the most ideal approach is to encode qubits into these two hyperfine states. And in this case, the qubit can live for a very long time in atoms, can basically determine the lifetime is determined by a vacuum. And only if you want, you actually should excite it to a Rydberg atom, for example, one of the states for a short duration. And there has been some pioneering experiments done both in Paris and in Mark's group in Wisconsin, but up to like about 4 years, 5 years, these, fidelities of this kind of quantum operations have been actually limited. And so the situation has started to change in 2019 with the advent of something which is called, we call it in Pizzagate, where Harry and Hannes, they basically kind of invented this very elegant protocol which basically allowed you to kind of imprint a conditional phase pi by just applying exciting atoms into Rydberg state with 2 short laser pulses. And actually, I'm not going to kind of go into details, but essentially this involves kind of a choreography on a block sphere such that, after the excitation for all of these initial state, the atoms always come back, but in this one case, they have this conditional phase. And actually, I think the day they had this idea, the next day they implemented it experimentally, and it was already working with reasonably high fidelity, with a rate in around 2.5%. And so already with this kind of system, we were actually sufficiently kind of enthusiastic to try some new ideas. And one of them ideas which we tried and which worked extremely well is this idea of reconfigurable quantum architecture. So the idea is essentially the following. So if you now store qubits in this hyperfine basis, they not only live for a very long time, but the atoms can be moved, used by just moving tweezers without disturbing coherence. And so basically, this is a simple example of that. So what you do here, you entangle pairs of atoms. So you can just check if they entangle by looking, for example, at the parity signal. Or instead of just checking them directly in situ, here what you can do, you can just move these atoms around, for example, across the entire array, and still check if they're entangled. And in fact, entanglement did not change at all. So basically, this gives rise to this idea of this kind of reconfigurable architecture, where essentially the connectivity of your system is itself a living organism. You can do some gates, move the atoms around, and proceed in this way. And so already once, in a kind of very, I would say, early days last year, we kind of, realized that it's a very powerful method, and we actually had a lot of fun creating various types of, states, cluster states, encodes, topological. Did a little bit of experiments on topological error correction. I will tell you a little bit about those. And actually, also, it turns out that there is a lot of interesting possibilities here to combine analog and digital evaluation. So let me just tell you a little bit about this. So basically, okay, so this kind of specific application is aimed to realize quantum error correction. So what is quantum error correction? So first off, it's something which most people believe will be needed if you want to have any kind of practical large-scale quantum information processor. And basically, it uses this kind of idea of redundancy. But in the quantum system, you have no cloning theorem. You cannot duplicate quantum information. So basically, this kind of redundant encoding essentially involves entanglement. So you take one qubit and spread it across several physical qubits, and then what you call this one encoded qubit, you call a logical qubit. So, and basically by delocalizing, make this degree of freedom potentially more robust, but also, of course, it's harder to manipulate it. So here is one example. So the prototypical example is of error correction, something which is called Tori code, where you start with the array of physical qubits living in a torus, which are sort of called data qubits. They will encode quantum data. And you have these additional red qubits, which are ancillars, which will be used to do what's called stabilizer measurements. They are basically kind of checks to check if you made an error or not. And so realizing this thing on a torus seems hard. And on a torus, basically, you have additional protection due to topology. But actually, what you can do, you can unfold this graph, and basically, this torus is equivalent to a planar graph, but with this kind of non-local connectivity. Some of these ends should be really wired, connected with each other. So we realize this non-local connectivity by using an old idea from Ignacio and Peter, where we were proposed to basically move certain qubits around to basically enable interactions between data qubits. So in our case, basically, we move the entire array. So this is an array of 8 qubits, which we move around, and each of this red circle is a quantum logic operation, CG gate. And now you see there is this long move across the entire array. So basically, in this way, we actually can create this toric code state. Basically, in fact, in this case, you have 2 logical qubits encoded one kind of going across one direction and another one another direction of the torus. And in fact, you can measure non-zero stabilizers and non-zero expectation value. For example, in this case, we prepare qubits in X state, but we also have access to the stabilizers. We know where error occurred, and we can, for example, do error correction or error detection to basically, in one case, correct one of the qubits really close to 1, and another one, not quite, but also pretty close. So these kind of, configurations, indicate that, there are some really new exciting opportunities which one can explore. In particular, really here you are not limited to this local connectivity, and you can really think about doing things in a kind of hardware efficient way. And, there are many exciting directions. So let me talk a little bit about what we've been doing recently. So we have now basically completed the third generation array. And so in this case, we have already implemented parallel multi-channel control. We can basically individually rotate atomic states for arrays, up to a couple of 100 atoms. So we have demonstrated some fast atom readout, but not yet integrated it in our system. I will talk a little bit more about this improving fidelities, and the way where it's kind of this work is going is to really start to doing hardware efficient error correction and detection, and in fact doing operations with logical qubits. So these are some of these pictures from generation 3 upgrade. So we actually can trap now over 1,000 atoms, and can sort over 500 atoms. But one thing which I'd like to focus in particular is the quality of operations, because if you grow the system size, you have to improve also the qubit fidelity. In particular, if you want, for example, to make these ideas of error correction useful, the fidelity of the gate should actually be larger than a threshold, which, for example, for the surface toric code is around 99%. And not only up to now, this has not been the case, but moreover, we did not quite understand where our errors come from. This is from the error budget from last year's paper, and there is one, for example, percent discrepancy. So basically, this problem has been solved by in two ways, by combining two elements. One of them is the new family of this optimal fast Rydberg gates, developed particularly by Guido Pupiu, and also there is a work by Hans Peter's group. And also another one is brute force technical improvement, just using higher power lasers, called the atom static traps and stuff like that. And so here is the result. So basically, in this case, we start with 20 atoms, split into 10 pairs, and we do what's called randomized benchmarking as a way to kind of, check how gates work. And then immediately, here we see that these fidelities actually exceed 99.5%. And once we have this pipeline set up, we can now just explore the entire family of the gates. So basically, the idea of this new family of gates is that, you basically have just one pulse, but you change the phase and time. But it turns out you can do it in many different ways. And And in all cases, you have quite high average fidelity. You also have pretty high individual fidelity. So each of these pairs, basically have very high fidelities, kind of almost without exception. And of course, one can now immediately, increase the system size. In this case, 60 qubits. Note that all of these gates are done in parallel, and then, again, all of these pairs, have very high fidelity. And so with this atom movement, of course, one can directly scale it to a much larger system. So this is how these Bell states look in the lab. So basically, so what we do here, prepare two types of states, and actually we always image, for example, atom in the state 1, and so there are always pairs of atoms, but here you see only single light up, and here only they light up in pairs. So this is basically kind of how we actually can really see and evaluate these fidelities. And I should say that this work together with a couple of other kind of recent breakthroughs, and some of them we'll hear from Manuel about, and also Jeff Thompson, and also some mid circuitry that really open a lot of exciting perspectives. So I would say we now understand these fidelities very well, that like things like 3 nines and maybe beyond fidelities are within the reach, and it's very, very exciting. So just to give what is maybe 2 minutes or so, just to give you a little bit of the kind of the insight where this work is going, let me just kind of talk a little bit how one could use these approaches to use efficient logical processing. And the problem here is the following. So once you delocalize this information, it kind of becomes hard, for example, to do things like gate operations. So you often have to do some kind of lattice surgery. So in fact, this delocalization length is also often called call distance. And so if once you start doing basically some operations, not only it's kind of it's involved because you have to do a lot of gates, but also it turns out that you have to actually do a lot of these parity checks. But actually there are other approaches, and in particular there is this idea of these transversal operations in which you can directly integrate the delocalized degrees of freedom. So what you can do, you can just bring this guys on top of each other and essentially apply the gate and bring them apart, and actually it turns out it's a very, very powerful approach because it's inherently fault tolerance. The errors don't spread within the block. It enables a long-range direct connectivity, but actually, most importantly, in this case, we basically can, treat all of these physical qubits as a kind of receiving a same instruction, and they kind of act as one of the one big atom. So basically, we are now thinking about logical qubit control instead of single physical qubit control. So here is one simple example. So in this case, we create 2 color codes, and it's done with this kind of simple circuits. And then one way to and so normally, when you do these circuits, you make an error. So one way to kind of make this preparation fault tolerant is to use one of these encoded blocks to check on the other encoded block. And effectively, what it amounts to is a Ramsey experiment done with logical qubits. So in this case, what we need to do, you actually need to rotate. You need to apply Hadamard operation on this upper one, rotate it in a X basis, and then bring them together and basically do this transversal synod, and then bring them apart, and then basically measure one of these qubits. If you measure this one of these qubits and actually it's still in a 0 state, with high likelihood that this other one should be in a 0 state. And in fact, that's the basis for this kind of fault tolerant preparation. And indeed, what you immediately see that it approach works very well. So for example, in terms of preparation, already this kind of logical encoded qubit, the fidelity is better than that of the physical qubit. And actually, if you do, then at the end, you do decoding, you do error detection, basically you don't see any errors at all. And experiments like this have been done with 1 or 2 qubits, with ions in particular, but this data actually corresponds to multiple pairs done in parallel. So in this case, 4 pairs of these color codes, are operated in parallel. And of course, once we have multiple, pairs and multiple encoded qubits, we can start doing algorithms. So here is kind of a very kind of simple first example. So in this case, what we do is we first prepare, a number of these logical qubits fault tolerantly, and then do some operations. For example, entangle, create a GG state, and basically it's again very early results. So this is the case where you don't do this error correction, don't do fault tolerant reparation. Here you do fault tolerant reparation, so you basically already break even. And again, if at the end when you do decoding, you basically only post-select on all stabilizers being correct. The fidelity is basically 1. So just to kind of give you a sense, of what is involved in this. So here is a movie which actually shows how this kind of small algorithm is performed. So it basically involves moving qubits between different zones, storage zones and entangling zone. It's kind of, it starts slowly, and then, the action starts, big atoms starting to move, and then eventually you do these logical operations. Actually, this is a movie which is kind of showing done with the experiment, qubits, and you kind of can maybe get a little bit of the feeling already now that what is really emerging is this kind of, the full kind of processor architecture. It's kind of a zoned approach where you have some stored logical qubits, some, number of fresh unsealer, some gate zone, and some readout zone. So I think I used up my time now, but, so I wanted to tell you a little bit about what's happening at QuEra. So they also had a big year because basically, as I already mentioned, their machine, became available on the cloud. And it's actually apparently it's relatively easy to program. So basically you can define system geometry, define pulses which are applied, and then you can run it. And as I already mentioned, there are actually quite a few papers already have been published. I think this kind of availability of this machine really heralds a bit of a new era, because you can experiment with that, you can make some discoveries, and they're looking for new team members, partners, and collaborators. So I think I used up my time. So with that, I'd like to thank you for your attention and thank all these people whose blood and sweat resulted in this.
Thank you very much, Misha.
So I remember you showed us the presentation in terms of the fidelities.
Yes.
And you also looked at the correlations of the errors, because a lot of
Yes.
cycle theorems.
Yes.
Like
Yes. There is if you are interested, we studied it in great details, and there is like a cool supplementary information chapter about it. So, and there are some small correlations, but they are very small, and they are basically very low rate. So, and they are mostly due to the fact that, for example, if the atom, so one of the errors, dominant errors, is actually a leakage error, where the atom, Rydberg atom, basically goes to the step which is dark, right? It can affect the nearby pairs. So, and this is a dominant source. But it's very small, and we don't think it will be a problem. You can also, it will limit, it will limit things like density with which you can do things in parallel. But as you already have seen, we can, the data I showed we can do on 60 atoms, we can now do on over 100 atoms, in parallel. So. Yeah.
Sorry.
Yeah.
It's not a bit of a naive question, but when you were doing your independent sets benchmarking, what did you vary to change the graph? Is it the spatial arrangement of the atoms that changes because you optimize it over many different graphs, right?
Sorry, for when we did optimization.
So you have these benchmarking graphs like the one that's on the slide here, and each of these data points has.
So this one?
No, to the left.
To the left. Oh, no.
Yeah.
Yes. So what we did, the graph is encoded in position of the atoms, and then you optimize basically the tuning and radio frequency kind of pulse profile.
Yeah.
That's what you.
So when you change the graph, you're changing the spatial.
We change spatial, and we can also change blockade radius, of course, connectivity. Yes.
this transport operations, what sets the limit for how much transport you can do, how many starts and stops, or the total distance, or the total quantity?
Yes, so it's actually it's an exceptionally kind of robust operation, and basically the only kind of thing, and so we already use a bit of an optimal control. So, and actually, if you think about it, the speed, it does not, so long as it's constant, it doesn't matter. Actually, acceleration, you can also compensate. It's a jerk, which is kind of, but you can use optimal control. And so basically, eventually, what limits it is that, if you do a lot of moves, you lose the atom. And to be maximally honest, we have not really pushed. I mean, we can make thousands of moves. We haven't really pushed this. And basically, if you start losing atoms, you just kind of optimize, move a little bit slower. So that's a consideration. So it actually was a surprise, but it turns out that this atom transport is extremely reliable. So the only maybe sort of downside, you can say, there is some speed limitation. So it takes sort of 100 microseconds in practice, and given it depends on trapping depth, trap depths, and so on. But it takes kind of 100 microsecond time scale to move the atom around, across the entire array, and it scales only very weakly with the size, and you could say, well, this 100 microsecond is, is a relatively long time. You would like to improve it, but what you gain, what you gain back is this kind of non-local connectivity and super efficient control, where you basically, with one control knob, you can move the entire logical to be something very, very special.
So, is in the long distance interaction problem the one I got the more six problem or
okay, there are different types of long distance. The fact that we can move the qubits around, this is not a problem. This is a big feature, right? So, but what the fact that you have this, this little tail, and this is something that so it basically determines 1/6 is actually not too bad. 1/3 would be worse, but 1/6 is not too bad, and basically determines effectively the density of, let's say, pairs or triplets. So we actually also did, I didn't show it, but we could do multi-qubit gates on multiple. But it determines how like the density of these clusters on which you can operate. And for example, but there is some optimization. So for example, in this analog kind of experiments, people often go to n equals 60, n equals 70 or something like that. But for example, for these gates, sort of like this data was for n equals 54, I think. So basically going to lower end. So I mean, there are these things, but yes, but these are, but it's already at the current state, as I say, we can operate on hundreds of atoms in parallel, which is actually kind of unprecedented.
Okay, maybe while Manuel sets up, we can answer one last question.
Yes. So for this maximum independent set problem,
Yeah. Yeah.
This Fourier square scaling. So if you talk about graph with hundreds of vertices, looking at this, the actual problem graph is probably much smaller, which can then be easily solved with the classical algorithm. So there is something with that.
No. So these are the graphs. No, there is one. The size of the graph is basically determined by the size of the the number of atoms determine the size of the graph. So the graphs which we are solving actually involve at this point hundreds of tortoises, right? So I mean, this graph which we have so far worked, all could be solved classically. So we can only look for sort of scaling advantage. That's the square root. And it is true. You are completely right. If it's square root, it will be quite challenging to get like practical advantage. But there are, but we are now looking at instances which are, slightly different, which